it's our pleasure to listen today to David Lhuillier. He's a physicist at the Department of Nuclear Physics at CEA Irfu. David has been working since the year 2000 on the physics of neutrinos from reactors. He has worked in the experiment double chose. And then he has developed a project for non-proliferation for using the neutrinos to survey nuclear reactors. Then he has been working in the stereo experiment, which the aim was to search for the sterile neutrino. And no more recently, he is working on the detection of neutrinos with cryogenic detectors. And in 2011, he received the Prix Joliot-Curie, the Joliot-Curie Prize. So today he's going to talk about precise measurements of fission neutrino spectra. This will be dealing with the stereo experiments and also not only this, but also the implications of his studies on nuclear data. So thank you very much, David, and now we listen to you.
Thank you, Beatrice. So thank you for the invitation. Yeah, so I will present you today some recent measurements of high accuracy that we performed on the fission neutrino spectra. And oops, sorry, it's not. Okay, I will start with some very basics physics that you probably all know about, but it's still interesting and useful for the rest of the presentation. So, as you know, neutrino started in the head of Pauli in the 30s to resolve this problem of energy conservation in the beta decays. What was visible in the final state was just an electron, two-body decay. So you expect single energy for the emitted electron, and people were measuring continuous spectra. So the hypothesis was that a new particle could be there, very difficult to detect because nobody was seeing it, but then sharing the energy between the electron and this new particle called neutrino to explain the observation. And the theory was written down by Fermi, kind of extension of the electromagnetic interaction, just using two currents, a leptonic current and a hadronic current, and coupled with a point-like interaction, described by just a coupling constant, the Fermi constant at GF. And then, so these two currents here that are interacting are describing the electron capture here. But then you can play around with time reversal and charge conjugation symmetry. Then you have the neutron decay with the same kind of contact point interaction between two currents. And also another process that we will talk about is the inverse beta decay, where you have an antineutrino interacting with a proton, and in the final state, you have a neutron and a positron. And that will be the process that the physicist will use in trying to detect neutrinos. So from this theory, it was quite a success because you have a phase space factor that, with momentum and energy dependence that gives you basically the good shape of the observed spectra. Some Coulomb correction due to the fact that the electron is escaping from a charged nucleus, and the coupling constant that you can tune from the observed lifetimes of the decays. And what Fermi got is a very low value. So the interaction of the neutrino is indeed very, very small. You have an interaction cross-section at the MeV scale that is 10 to the minus 44 centimeters square, okay? That would explain why nobody noticed this neutrino before. We have to wait for the 50s before people try to really propose experiments to detect neutrinos. And the famous physicists, Reines and Cohen, they first proposed a kind of crazy experiment. It was back in the 50s. So many different trials to develop the nuclear bombs. And so they were just proposing to detect the burst of neutrinos coming from the burst of fission in a nuclear explosion. And what they were proposing is to dig a vertical tunnel that they would put under vacuum, and they will leave the detector free falling at the moment of the explosion, so that the shock wave will not disturb the detector. And then you have a mattress of feather and rubber at the bottom of the tube. And once the radioactivity is going down a few days after the explosion, they could retrieve the data. Just computing all the numbers, they were missing like something like 4 orders of magnitude to run the experiment, but they got approved. It's, still during they were digging this tunnel actually, but other colleagues proposed to really look seriously as another way to detect neutrinos, which was reactors. Because they were known to be also, of course, very intense sources of neutrinos. And so they made the first experiment at the Hanford reactor that was kind of seeing neutrinos, but not conclusive enough. And so they came up with an improved experiment at the Savannah River reactor. They installed a detector at 11 meters only from the core, which is still a large flux of neutrinos. You see 10 to the 13 neutrinos per centimeter square per second in the target. They put this setup with underneath a 12-meter overburden to protect against cosmic rays, because at that time already they understood that this final state, a positron and a neutron, could be mimicked by cosmic rays. So you have to protect against them. And this 12 meters of overburden was already quite something. And then the target, so again, antineutrino interacts with the proton. The proton, you get them from the water, the 2 blue volumes that you see here. Then the positron will annihilate emitting gammas that we detect in liquid scintillator volumes that are sandwiching this water volume. And the neutron is captured on cadmium that is diluted in the water. And again, emitting gammas that will be detected by these big tanks of liquid scintillators. And they make heavy use of all the information of this very particular process that is the inverse beta decay. The positrons annihilate with 2 back-to-back 500 keV gammas. So you expect 500 keV energy deposition on both sides of the target. Then if the neutron is thermalized and captured on the cadmium in the water, a few 10 microseconds later, you expect a gamma cascade from the de-excitation of the compound nucleus. So really extensive use of the energy correlation, space correlations between these two particles, and even time correlation, because you know that the neutron will take like 10 microseconds to thermalize. And this is a copy, a photo of a real event that they recorded on a scope, where you see the 3 liquid scintillator tanks, 1, 2, 3. Here, the interaction happened in the volume B, and you see the 2 last liquid scintillator volume with the 2 500 keV signal and the gamma cascade for a few 10 microseconds later. With this kind of tricks, they were able to reach a signal-to-background ratio of 4, which is quite an achievement. Even today, when you are close to surface, reaching this kind of signal-to-background ratio is nice. And they are clearly laying the basis for the detection of reactor neutrinos for the next 60 years. What about comparing with the expectation? So they had actually some prediction of rates, and there was a 5% agreement between their results and prediction. Turned out that actually Fermi's prediction was wrong by a factor 2 because in what I was showing before, the parity violation is missing. They learned about it 1 year later. That's a factor 2 in the interaction probability. But it turned out that actually the estimation of detection efficiency was also wrong by a factor 2 from the experimentalist. And we can also wonder how they were able to predict the neutrino flux and spectrum that was emitted by a reactor. So that's how it works. Sorry. So from a fission, here the fission of U-235 isotope, you have fission products that will evolve towards stability by beta minus decays only because they are neutron rich. They want to convert the excess of neutrons into proton. Beta decay is very efficient for that. So it's a pure source of anti-electronic neutrinos. Only those type of neutrinos are produced by beta minus decays. The energy is clearly in the MeV range. That's nuclear processes. And for 1 gigawatt of thermal power in a reactor, you get 210 to the 20 antineutrino per second. A huge source, most intense. That's the most intense man-controlled source of neutrinos. If you want to predict the spectrum, well, you just multiply the neutrino spectrum per fission by the number of fission. That's the, okay, so far easy formula. Gets a little more complex when you take into account the evolution of the reactor fuel in time, because fission of the U5 isotope is not the only process. You know that part of the neutrons that are emitted after the fission get captured by the dominant U238 isotope that is present in the core. And from this capture reaction and beta decays, you end up with plutonium isotopes, and especially the plutonium 39, 239, and 241 that are also fissile isotopes, and they will contribute to the fission. You accumulate plutonium in the core when you are running the cycle, and this plutonium isotope contribute to the fission. So now this equation gets a time dependence. The energy released by plutonium isotopes is higher than for uranium. So the number of fissions for the same thermal power, the number of fission will decrease over time. And then it's not a single neutrino spectrum per fission that you need, but you need to sum over all the fissile isotopes, U5, PU9, PU41. And also some part from the U8 that is also fissioning with fast neutrons. So the final formula will be something like that. The first term is still the number of fissions, and the second term is your sum of neutrino spectra per isotope, weighted by the fission fractions. That's the evolution of fission fractions versus time for one typical reactor cycle. You start with a majority of U5 fission, but the more you are when time flows and you operate the reactor, the plutonium is accumulating and contributing more and more to the fission. That's the blue curve. At the end of a cycle, you have almost shared contribution between U5 and PU9. All these terms in the equation, you can get them quite accurately. The power, you know how to make the enthalpic balance at the level of the primary circuit of a reactor. Alpha coefficients, you can get them from reactor simulations. There you can reach, like, let's say, like something like a 5% accuracy. But you have large correlation between those fractions because you know that the total power has to be always the same. So actually, even few percent uncertainty there is a subdominant contribution in the total spectrum and flux of neutrinos that is emitted by the reactor. For the number of fissions, you need to divide this thermal power by the energy, mean energy per fission. You need the mean energy released per fission per isotope. And there you have some subtleties, but you can get quite high precision. So really the challenge is to predict this neutrino spectrum per fission for all the isotopes. One important remark, what I've been explaining here is for commercial reactors, where you have a low enriched fuel, and you have this process of accumulating plutonium. In the research reactors, the fuel is highly enriched in uranium. It's 20, even up to 90% enriched in U5. So all fissions remain fully dominated by U5 during all the cycle, and you won't have this kind of evolution in research reactors. Okay, so let's see what is inside this SK, this neutrino spectrum per fission. So you have to, so you remember from the previous scheme that the neutrinos are emitted by the beta decays of the fission product. So you have to sum up the activities of all fission products. But one specific fission product is itself the sum of many beta branches with different branching ratios linking to different excited states of the daughter nucleus. And even if you look at one single beta transition, it's itself quite complicated because you recognize here the Fermi theory, the same phase factor I was talking about before, the Fermi function for the Coulomb correction, some normalization. That's only for allowed transition. If you have a forbidden transition, you have shape factors, quite difficult to compute. And then you have all kinds of corrections due to finite size of the nucleus, radiative corrections, and so on. And you have to do that for hundreds of nuclei, thousands of beta branches. It's quite reluctant. And then from the beginning, you know that you won't be very precise because you are missing data. And the more unstable, exotic the nucleus is, the scarcer the data will be. So what people did to get around that is to measure the total beta spectrum, not neutrino spectrum, but beta spectrum, this time electrons coming from fissions. And actually, this kind of measurement was available already in the 50s. And that's how they made it for the very first time. They exposed the foil of fissile isotopes to a neutron beam. And then they were able to detect the beta electrons in some detector close to the foil. So this way, they were able to get a first total spectrum of all the beta electrons that were emitting from the fission of U5, for instance. And they converted it into neutrinos, assuming that in that distribution, all the many branches with different endpoints, they had a kind of Gaussian distribution of endpoints, completely unphysical, but it's okay, why not? That's all they had at that time. So they assumed that all the endpoints were distributing according to a Gaussian, and then they used this distribution of endpoints to convert into neutrino. And that's a difficult problem. It is ill-posed from the beginning, and because you have only the total spectrum, and you don't have access to information of the many beta branches that are contributing to this sum. If you want to do it rigorously, exactly, well, you can apply the energy conservation at the branch level. This is a beta branch, the electron spectrum. And if you apply energy conservation, the energy of the electron and the neutrino is always equal to the endpoint. And so you have a kind of mirror symmetry at the single branch level, where you can deduce from the electron in red, you can deduce the neutrino spectrum in blue. But if you do that for one single isotope, here it's manganese 56, for instance, that's the red spectrum. You can try whatever mirror symmetry around whatever point, it won't work because the correct answer is the blue spectrum, where you see that the different branches contributing to the total spectrum have quite some impact in the shape of the neutrino spectrum. So you really need to access the information at the single branch level. If you have only the total spectrum from many branches, that's a difficult problem. So that's why they came up with this Gaussian model of distribution of endpoints in the fission beta spectra. A major improvement arrived in the 80s with Klaus Streckenbach and colleagues at the ILL reactor in Grenoble. So this is a cut view of the ILL reactor. You have a huge neutron flux, thermal neutron flux. There was some pipe here at the bottom of which you could insert some foils of fissile elements, so uranium-5, plutonium-9, plutonium-41, etc. They were exposed to the neutron flux, fissioning, and so part of the beta electrons could be just a line in this thin tube and then get analyzed in the magnetic spectrometer. So very accurate measurement of the distribution, the energy distribution of the beta electron. So that was a new and very accurate measurement of beta spectra, again, for the three main fissile isotopes, U5, Pu9, and Pu41. And then they were still facing this problem of converting from beta to neutrinos. But what they did is to assume some virtual branches, okay? They know that there are many, many branches to build this sum, this beta spectrum. They were just fitting the spectrum with 30 virtual branches, 30, 35. With this amount of branches, you have enough bins first to fit all the parameters you need. And you are really able to go through all the points. It's a very accurate fit of the form of the beta spectrum. And you use this kind of virtual branches. They do not correspond to actual real transitions, but still their sum is exactly fitting the electron spectrum. And now at the single branch level, you can convert every branch from electron to neutrino, and you sum again all the 30 virtual neutrino branches to predict the neutrino spectra. And this kind of procedure, you can test it numerically. You can use all the ENSDF database, for instance, build up a spectrum with thousands of branches and test this procedure. And you see that actually the numerical precision is quite good. And that was quite a breakthrough. People started to be convinced that you could have prediction at, let's say, 10% level and start to do some kind of accurate physics from that. So it was opening the door to, first applications to reactor surveillance. I won't have time to talk about that today, but also fundamental physics of neutrinos. If you have a good prediction, then you can look for distortions around that prediction, and especially look for the oscillation phenomenon. So here you see the three emitted spectra for the three fissile isotopes. This is log scale. If you go to linear, it's a kind of exponentially decreasing spectrum. And the cross-section, the interaction cross-section for the inverse beta decay process is quadratic with the neutrino energy. So when you multiply the black and the red curves, you end up with this blue curve that is peaking around 3-4 MeV. That's where you will detect most of the neutrinos. Far less neutrinos at low energy and far less neutrinos at high energy. And that's the curve that you get for the three isotopes. There you see that actually U5, per fission of U5, you expect to detect more neutrinos than for a fission of Pu9, just because of the different fission products, different beta transitions that are involved in the two processes. Okay, so the goal now is to make fundamental physics about neutrinos using this accurate prediction of fission spectra from these high-level measurements, the conversion of the beta spectra into neutrinos. A few words about this phenomenon of neutrino oscillations. You start with a neutrino that is emitted by your reactor, so you talk to the interaction space, okay? So when the interaction, here it's a beta decay, you know that what is coming out of the reactor is an anti-electronic neutrino. And then you want to detect this neutrino somewhere in your detector, further away from the reactor. And the inverse beta decay is also sensitive to this unique flavor of neutrino that is anti-neutrino of electronic flavor. In between the two, the neutrino will travel, and you expect that, okay, an anti-neutrino is an anti-neutrino, it just travels. But you have this freedom that the interaction space that is talking with the flavor, electron, muon, tau, this is the three active flavors that we know. They matter for the interaction. For the propagation, what matters is the mass eigenstate of the Hamiltonian. So you have a new basis, new 1, 2, 3, that are the mass eigenstates. There is no constraint, no symmetry of physics, no fundamental laws that imposes you to have the same states in these two bases. You can have a rotation between the three axes, I would say. So this matrix here is just a standard rotation with the cosine theta and sine theta. And you have three possible mixing angles to go from flavor to mass eigenstate. Why doing that? There is no fundamental reason as far as I know. This is nature does it because it can do it. This is not violating any fundamental symmetry or conservation law. And so once you have in the mass eigenstate basis, you project your physical state, your flavor state into mass eigenstate, then propagation can differ from one state to the other if the neutrinos have mass and different masses. Then they will propagate in a slightly different way. And when you recombine again, when you project again in the flavor space for the detection, that's what you do when you detect, then you have a different composition of your wave packet because of this propagation and this because of the different mass of these states. And so what you project back, even if you started with a pure anti-Newey state, what you will detect now is not pure anti-Newey. You will have a fraction of the wave packet that can give you a muon neutrino or tau neutrino. And so what will happen if this process exists is that you emit pure anti-neutrino of electronics flavor. You detect only this same kind of neutrino. If you have this oscillation phenomenon that is occurring, then you will miss part of your initial flux. And what we are doing when searching for oscillations at reactor is that we are doing disappearance experiment. Check if part of the flux has disappeared. How does it disappear? Well, it's a simple math, because again, this matrix here is just a rotation, and here you have simple simple equation in the propagation of particles. At the end, the probability to remain an electronic antineutrino is 1 minus something. And you have the amplitude of the phenomenon that is driven by the mixing angle, that is sine square 2 theta. And the frequency, you end up with an oscillating phenomenon. And the frequency is driven by this ratio, the difference between the square masses of the two mass eigenstate, the distance traveled between the source and the detection, and the energy of the neutrino. It's really a sine pattern. You expect started with 1, then you disappear, you back to the initial spectrum, disappear again, back to the initial spectrum, etc. As long as you travel away from the source. One very nice example of that is the Camland experiment. 1 kiloton of ultra pure liquid scintillator that was installed down in the Kamioka mine in Japan, 1,000 meters underground. That was before the 2011, the accident of the Fukushima. So they had many reactors around, and most of them, the closest, were around 180 kilometers away. And so they made the effort to follow all the history of this reactor and predict how many neutrinos they were expecting and with what energy distribution. And they compared their data with this prediction. And what they did is to group the data in bins of L over E, because you remember that's the oscillation phase of the oscillation. It's delta M square L over E. And so if you plot the data in that bins, you expect a sine square pattern where you start from 1, disappear, go back to 1, disappear, go back to 1, disappear, etc. What you see is that it's never going back to 1, and the amplitude is kind of fading out. So it's kind of, there's a damping factor. And this is due to the resolution effect of the detection. If you look at the uncertainty on the phase of this oscillation, the more you travel, well, L increases, you get more and more sensitive to delta E over E, your resolution. At some point, the uncertainty of your phase is comparable to 2 pi. So you are just seeing the average of the sine square, which is the average of sine square is one half of the full amplitude. So that's why you see some amplitude remaining and then damping, and at the end it will flat out at a level that is 1/2 of the full amplitude of the phenomena. Still, it's a very nice pattern, very characteristic of an oscillation. It was one of the most beautiful measurements. It was crucial in the measurement, in the accurate measurement of the parameters that are driving oscillation in what we call the solar sector. And these parameters are important for the explanation for the oscillation of the solar neutrinos. Still, it remains quite challenging to control your absolute normalization there. You need to know what is the absolute normalization of your measurement and absolute normalization of the prediction so that you can compare the two. So in recent experiments, what people try to do is to get rid of this prediction and go with relative measurements. One typical example is the double show experiment that we proposed in France at the Show power plant in Ardennes, in the north of France. And there, the idea is to have two identical detectors. The same detectors, you build twice the same large apparatus, and you see the human scale here. One at few hundred meters from the course, the two cores are here. And another one that is further away, like 1 kilometer, that is, this distance has been chosen because it is expected to be the first minimum of the oscillation that we wanted to measure. This idea was also used by other collaborations in Asia, in Korea with the Reno experiment, in China with Diabe. And you see what they were doing is just taking the ratio of the neutrino spectrum in the far detector to the near detector. So the near detector was acting as was replacing the prediction. You measure your spectrum shape and normalization in the near detector, and the extra distortion created by the oscillation is measured in the far detector. Just taking the ratio, you see the three different experiments. They all have a bunch of near detectors, few hundred meters away, where the oscillation has not started. And then the far detector is probing different points of the first oscillation, and this first minimum that will get back to 1, and etc. And all experiments, so you have slightly different pattern because they probe different places in this oscillation pattern, but they are all very well compatible with oscillation shape. And that was a very nice measurement of the last unknown parameter of this neutrino oscillation, which is the θ13 mixing angle. It is the smallest angle in all the mixing matrix. And it is now the most accurately known, actually, thanks to this kind of experiment. So very accurate physics. We are now knowing all the parameters of the mixing matrix, the three angles, the 2 delta m square. We are just missing this CP violation phase. That's another program that is going on. And with this approach, we almost get rid of the predictions. We don't need predictions at all to run accurate measurements. Actually, not quite, because what happened for the first phase of double show is that we started with only one detector. So because we could not build the two detectors in parallel, so we started with the far only, and so we kind of revised the prediction of this ILL beta spectra, the way they were converted into neutrino. I won't go into the details, but at the end, the prediction was changed by about 6%. And as a result, we went from a situation where everything was well understood at small distances. We had a good agreement between neutrino measurements and prediction. A first disappearance at 1 kilometer, that was the first mixing angle, θ13, and a very large disappearance from Camland from the θ12. And now the whole picture got shifted by 6% because of this new prediction. And this was our work was confirmed a few months after by an independent publication. It looked like all the measurements were a little bit below the prediction. So was it a problem with the prediction? So at this time, okay, again, two independent work. Everybody agreed that the prediction should be corrected from these biases that we had shown. In the data, it's difficult to believe that all the experiment has the same trouble in the normalization. Or the last hypothesis was new physics. And the idea is, okay, we are missing neutrinos. Well, we know about that. Missing neutrinos, we already had it here at 1 kilometer and 100 kilometer. And we could explain that by oscillations. And we know that if you are too far away, you don't see all oscillation patterns. They are smoothed out by the resolution effect, and you end up with only this formula that is one half of the amplitude, and the resolution effect is smearing all the oscillation pattern into a global deficit. So that was the idea, that maybe this deficit that we see at very small distance is from a new kind of oscillation that could occur at very short distance. And because they are at very short distance, when you measure them at 100 meters from the core, it's too late already. You already have access to the mean deficit. So and of course, that was quite an important physics case, because a new oscillation pattern requires a new type of neutrinos. All the mixing that have been measured before were saturating the possibility of oscillations away from a reactor. There were no space for extra oscillations. So if you want to add a new oscillation at very short distance, you need a new neutrino, and it cannot interact with matter. Otherwise, we would have seen it in previous experiment. So it has to be sterile, not interacting with matter. And these kind of guys have been around in the theory for long. They are good candidates for dark matter, for instance. And so it was very appealing for the community to check that. Is this anomaly coming from a new states of neutrinos? And so where could it be? What are the parameters of this new neutrino? Well, I show you here its possible domain of existence in a plane of the amplitude of the mixing. So the horizontal axis is the amplitude of the mixing of this neutrino with the electronic neutrino that we know that is emitted by reactor. And the vertical axis is the frequency of the oscillation. Okay. So the amplitude, well, the hypothesis is that this few percent, 6% deficit is the average of this oscillation. So what we see is 1/2 of the total amplitude. So the amplitude, the sine squared 2 theta, should be 2 times 6%, so around 12%. That's why you have a band centered around this value here. And then the delta n square, you know, that's it's the frequency of the oscillation. It has to be high frequency, because otherwise we would have seen large wiggles here in the data, and they are not there. So it has to be high frequency that are damped, smeared out by the resolution effect. That's why you have nothing here in the bottom part. That's the long oscillation, and these are in the upper part, the rapid oscillations. So this neutrino, if you put all the numbers, all the data available, all the uncertainties, and so on, this neutrino should live in that area. And then what was also quite appealing is that there were other anomalies in the neutrino field at that time, coming from a neutrino experiment using beta sources, very strong sources that were built from irradiation of chromium in reactors. People were 100% sure about the activity of the source. There are many different methods to measure it. They put the source in their detector and count the number of neutrinos, and they were also missing neutrinos in this kind of experiments. And the parameter of the neutrinos that you need is kind of well compatible with what we had from the reactors, actually. So clearly, there was a move in the world to look in an ambiguous way to a possible new oscillation signal at very short distance from the reactors. How much time do I have left, Beatrice? I'm not sure I started. I don't hear you. Okay.
Yeah, sorry, we started around 8. I think you still have 7 minutes or so.
Okay, so I have to
10 minutes maximum.
So just to say that in double show, I said that we took the near to far ratio, far to near ratio between the two spectra, and we had this nice pattern of oscillation, fully compatible with the theory. If you look independently to the near and the far spectra and compare it with prediction, that's what we had. A kind of deficit here in the area where you count most of the neutrinos, and this large distortion here. That was actually quite some departure from the prediction, but it was the same in the two detectors. That's the idea of the method. Maybe the prediction is wrong in shape and in rate, but as long as you have two identical detectors and you can prove that you control the response of the two detectors, all these distortions coming from biases in the prediction cancel out, and you are only left with the oscillation pattern. And so that's the kind of idea we wanted to apply in the most recent experiment. This distortion I was talking about in the around 5 MeV is not due to double show. It's not a bias of double show, because many other experiments were seeing the same, actually. It looks very large with respect to the deficit here, but you have to remember that the flux at 5 MeV is a lot lower than what you have around 3 and 4. So actually the rate, the impact on the rate here is a sub% level, while the impact on the deficit here is this 5-6% deficit that we have. So two anomalies, in a rate anomaly and a shape anomaly. And there was a quite large program to look at this, to look to this possible new pattern of oscillation. 6 different experiments all over the world to go very close to a reactor, like 10 meters, and check for this oscillation pattern or not. And I will just present briefly the stereo experiment that we installed at the ILL reactor in Grenoble in France. Why ILL? Because it's a compact reactor, like less than 1 meter. It's good to see oscillations at very short oscillation lengths. And it's a highly enriched fuel, so it's a pure U5 fission spectrum. We have access to pure U5. We completely decoupled from the plutonium contribution. And that's the 3D view of the experiment. You see here the core of the ILL, and we are very close to it. Underneath a water channel that was here in the reactor building, and protecting us. We have 2 meters of concrete and 6 meters of water to attenuate a little bit the flux of cosmic rays. And again, we follow the idea that I described before. Our identical detectors now are detector cells, 6 identical cells. We are 10 meters away from the core only, very short distance. And if this new oscillation is there, if the electronic antineutrino is mixing with a sterile neutrino, and with the parameter that I've shown you in this amplitude frequency space, that's the kind of distortion that you expect. Black is the prediction, blue is what you could have in the first cell 6 here. And red would be the distortion that you will get in the cell further away from the reactor, cell 1. And you see that you have clearly distortion in shape and rate, but the distortions move along the distance from the reactor, because that's this oscillation pattern with this sine square dependency. So it's quite unambiguous signal if you can detect this kind of distortion. It's quite difficult measurement. We are not in this. It's quite same spirit than the very first experiment I was presenting by Reines and Cohen. But now it's not a matter of discovering the neutrino. It's a matter of measuring the spectrum at the few % level. It's a different world in that sense. So we need a huge shielding to isolate the inner detector to all the outside background. And of course, we also use all the possible tricks to discriminate this inverse beta reaction from all the other background, using the capture of neutrons on gadolinium and this positron spectrum, the space, time, and energy dependencies of these two particles in the final state. That's the real picture. You see the scale. The detector on this picture is actually flying on air cushions. And we mounted it here, and we pushed it on air cushions to the final place that is underneath this big water channel that you see here to protect us against cosmic rays. And the reactor is somewhere here in the core of the reactor is here. It was really mandatory to demonstrate that we understood very accurately the response of our detector. We circulated many gamma sources, and the difference between simulated gamma lines, reconstruction of the gamma lines, and measured gamma lines, all the residuals, all the comparison are within 1%. It's not only gamma lines. We use actually these cosmic rays that you cannot totally kill them. There are always some rays left in your detector. When a muon stops in the liquid scintillator, it can get captured on carbon-12 and produce a boron-12 isotope that is a beta emitter with a very nice beta spectrum up to 13, 14 MeV. And it's continuous spectrum and all over the place, and it's completely homogeneously distributed in the target. So it's quite complementary to the gammas. And we were also able to really have a very nice agreement with the simulation. And we were able to demonstrate very high stability of the detector over time for all the cells. What we tried to do with this experiment is to go over the full analysis, full study of the anomalies through oscillations, absolute normalization, spectrum shape. And we were happy to publish our final results in the Nature journal. This is the data taking with on and off period alternated so that we can subtract the background. I think I have no time to discuss in detail the analysis of the oscillation pattern, but the important point is that thanks to the 6 identical cells, we were able to get rid of the dependency on any external prediction. We are just looking at relative deviations between the cells, and all the spectra from the 6 cells were actually compatible with each other, meaning that we have no signal at all of any sine square distortion that are evolving from one cell to another. So all these lines, these color lines that you see here, the solid lines is the contour set by the stereo experiment. Everything that is on the right of this contour is excluded. So a large part of this sterile neutrino hypothesis is excluded with high confidence level. Only the very high delta M square remains, but this would require very heavy neutrinos, and cosmology starts to be quite unhappy with that. On the absolute normalization, we were able to set also very accurate numbers there, which is quite difficult for a small detector and at the power reactor, at a research reactor, sorry. For the power, we were able to set this 1.4% uncertainty. That is quite unusual. And the last point important for the normalization is the detection efficiency. The fact that the neutron in the final state is captured on gadolinium, that induces gamma cascades in a small detector. So we are very sensitive to energy leakages. And that's the first link with nuclear databases. We use this fission code that is combining Ripple-3, EGAF databases, and then level density models of level density and radiative strength functions to really predict accurately all the possible gamma cascades from gadolinium. And we replaced these, we used these predictions instead of the standard Geant4 simulation. And we were able really to improve the agreement between data and simulation and reach this 0.7% uncertainty in the detection efficiency. So at the end, we have a very accurate measurement of the total flux of neutrinos, and we confirm the deficit, about 5.5% here from our own experiments. If we take all the previous experiments and take the world average, it's about 5% deficit coming in this pure U5 fission spectrum. And we have also the spectrum shape, of course, since we have a very good understanding of the detector response, we can merge all the cells together, get the full statistics, since we know that they are compatible with each other. So we merge everything. And we made also the effort to correct for all the detection effect so that the energy that we provide is the true antineutrino energy, the energy of the incoming antineutrino, not the detected energy with all the resolution effects. And this has been shared with the community in some repositories. If we compare with the prediction, we confirm what the power reactor, this with a mixing of uranium and plutonium we are seeing. We have a deficit, global deficit at in this energy range where we have most of the neutrinos, and this local distortion here. So if I have a few more minutes, I would like to comment a little bit about, okay, so what's wrong? We have a global deficit. We do confirm with high precision this local distortion in shape. But this distortion is not oscillation pattern because it is there for all distances, for all reactors, for all detectors. So it's clearly not oscillations. It's a common feature that is there in the fission spectra, and that was missed by the initial prediction. And still, we don't see sterile neutrinos. Also, we reject that hypothesis. So what was wrong from the beginning? And the global picture is the following. This is the prediction from this converted beta spectrum and the conversion from the total fission beta spectrum into neutrino fission spectrum. So this is the 1-1 reference. This is the ratio between prediction and measurement for the U5 on the horizontal axis and for PU9 on the vertical axis. So the model, the prediction by definition is centered around 1 with the 2 sigma error bars here. And neutrino data are clearly saying that, yes, there is a deficit. This is the pure U5 average from the recent experiment. This is the ellipse from all the other measurements at power reactors. But it is not clear, well, at least U5 is taking most of the deficit. Maybe it is the only contributor. Not clear if the plutonium has a deficit or not, but actually what is really pinning down the uncertainty is this interesting new measurement by Kopeikin et al. In this publication. They were measuring the ratio between uranium and plutonium spectra with a new device, quite complementary to what was done at ILL. They have alternative target of plutonium and uranium in this disk that is rotating. The neutron beam hits the target here, and then they analyze the beta spectra in this detector. And since the wheel is rotating at high speed, the detector is stable enough between the alternance of uranium and plutonium, and they are really able to measure accurately the ratio between the two isotopes, even if they do not control very accurately the response of this detector. And at the end, they say, okay, there is a 5% shift in the ratio between the prediction and our measurement. So the best explanation now is the following, is that when doing the measurement, this total beta spectrum measurement at ILL, they were normalizing their neutron flux by using gold and lead targets. And they were using conversion lines from these targets induced by neutron captures. And actually, because of several measurements, the measurement of uranium that makes reference, that is taken as the reference, is the last one. And they switched from gold to lead only for this measurement, which was probably not a good idea, so that this measurement is not correlated in normalization with the plutonium. And probably the nuclear data of this reaction have some bias, not clear from the latest measurements, plus the fact that the conversion coefficient is not measured but calculated. But it is clearly a good candidate to explain why only U5 has a deficit with respect to prediction. And to finish, a few words about the summation approach. I was explaining at the beginning of the talk that it was quite painful approach, many beta branches, many nuclei to sum up, to try to have a prediction. Since the 80s, there was impressive amount of nuclear data collected. It's quite impressive to see how much information you have in these databases. And we have latest calculation estimating and propagating all the uncertainties. That's the green ellipse that you see here. And actually, you see that these new predictions reach an accuracy that is quite interesting and kind of confirming this scenario of deficit moving left deficit in the U5, but not moving much vertically, so no clear deficit on the plutonium side. And this other calculation, there is no uncertainty estimated, but still it is a huge effort in gathering and measuring again many different isotopes to correct for the pandemonium effect. The pandemonium effect is a bias that we know that is there in the databases for beta decays. We are missing the connection, the beta decays toward the highest excited state of the daughter nucleus because of the way gamma transitions were measured before with high resolution and low acceptance, low efficiency gamma detectors. People are now developing measurements with total absorption spectrometer so that you don't miss all the gammas of this cascade and correct the beta filling. And this is really promising approach and converging to very nice results. Now you see the evolution when people were gathering more and more corrected nucleus and putting that in their calculations. We are now converging with the data. This is the evolution of the neutrino rate versus the amount of plutonium in the core. And this is a prediction of the spectra for the different isotopes. And you see quite nice agreement in shape and only a deficit for U5. Again, quite coherent with the neutrino data. And that's my final slide. If we want to push further here, each time you want to correct a nucleus, an isotope, you have to make a measurement produce the unstable nucleus, implant it on in some detector, make the measurement. It's a quite long program. The attempt that was done here is actually to extrapolate these corrections with a very crude, basic, effective model to correct the level densities predicted by macroscopic calculations. A single parameter that was actually adjusted, tuned to fit the available tags data. But then we apply this correction to all nuclei. And doing that, so that's the kind of red band that we obtain when comparing this kind of prediction with the previous prediction. And you see clear deficit and local distortion that is in just amazing agreement with the neutrino data. One more hint pointing to the importance of the correction of the pandemonium data and the interest of this neutrino data to guide the correction of nuclear data. And I will stop there. I think I was already very long. So no sterile neutrinos. If you combine, I talked about stereo, but if you combine all experiments, the contour is very covered with high confidence level. And in the next generation of experiment, everything will be covered, even this very high delta M square region. We provided reference spectra with very high accuracy from stereo. That was one of the leading experiments in the field. We made a global common analysis with Prospect. That's another experiment in US that also gave very nice results. So we combined our two measurements to gain even more in accuracy for pure U5. And there is work ongoing to combine with the Diabe experiment, which is at the commercial reactor, combining uranium and plutonium. So we are in the process of combining these three experiments to really get the most from the data. And that's our legacy, I would say, to the community. And it's quite amazing to see that now the accuracy of the neutrino data are kind of superseding the accuracy of some nuclear data, and they can serve as guides to correct or to improve the quality of the beta decay nuclear databases. And I think that's a nice way since the earlier 50s. I think that there were improvement of accuracy was going back and forth between nuclear physics and neutrino physics, and I think that's how we are doing progress in fundamental physics. Thank you.